Okay, so hi everyone, welcome to our tutorial. I am Nikos. I'm a PhD student at Northeastern University, and I will be presenting this tutorial together with my advisors, Wolfgang and Mirek. The title of this tutorial is Toward Responsive DBMS, Optimal Join Algorithms, Enumeration, Factorization, Ranking, and Dynamic Programming. So we will be talking about many exciting techniques at the forefront of evaluating joins optimally, and the slides of this tutorial will be made available afterwards in our in the website linked here. Also, during the presentation, please use the chat for questions, and we will also be having 30 minutes after the tutorial to discuss if people are further interested after the tutorial is over. So I will start by with an introduction. So first, what is this tutorial about? Why do we say responsive DBMS? So database systems can often become unresponsive when we submit a query, which means that they don't return anything in the output for a very long time. This is particularly true if the query contains many joins, since we know that the join is essentially one of the most expensive operators in a database system. But often we're not interested in the actual output of the join, but rather in some task which we describe here with this function f over the join. And some examples of such a function is, for example, to count how many answers we have, or if we have a ranking function to find the top k answers of the join, or let's say to find the median, and so on. Now, database systems are very slow for this task because the standard strategy is to first materialize the join and then perform this task f over it. And the join result can be very big. So what can we do about this? One way to cope with this problem is to push f into the join, if we think of f as an operator. So basically here, what we're trying to do is to perform f without first materializing the complete output of the join. A second strategy, which is very relevant if the output of f is also very large, is to enumerate. So even if the output is very big, after some pre-processing time, we can start returning something back to the user very early, followed by the other answers, ideally in quick succession, even though all the answers are not available yet. Now, there is a bunch of relevant concepts that are relevant for this vision to be possible. And part of what we want to do in this tutorial is to explain what these techniques are and what is the relationship with many different tasks. So basically, we have a toolbox of techniques that we can apply to many different queries or tasks, and these are quite general in the sense that they are not made for one specific task. Okay, so now let's do an overview of what these queries or tasks are. So the queries that we are interested in are those that have joins. So basically, it's select from where query in SQL, where we can also have projections. So some columns can be projected out after the join, and we can also have selections. For example, some column can be compared with a constant. To formalize this, we use the language of conjunctive queries. And in data log notation, this basically looks like this. This is an example. And here you can see we have some relations from the database, R1, R2, R3. We also have equijoin conditions, which are encoded by repeating the same variable between the relations. We have projections by essentially having some variables here that do not appear in the head of the query. So here we only keep x1 and x2 and project out z1. And we can also have selections by equijoin selections by having numbers here. And we will call full conjunctive queries the queries that don't have any projections. an example of a query answer here is to find values for the variables, which are essentially the columns in the database that satisfy the formula. So here 1, 3 is a query answer. Now, the first task that we are interested in is to perform some aggregate operation over the output of the join. Some examples of that is, for example, to count, as we said before, how many answers the query has, or let's say if we have a graph to find a graph pattern that has the lowest weight, let's say a 4 path in a graph, or if we imagine that every input tuple has some probability of being true, to find the answer with the highest probability. And also something we may want to do is, we may not care about the output at all, we may just want to know if there is any answer. And all of this can be seen as some aggregate over the array of produced by the join output. Now this array, we don't actually want to create it, but in order to understand semantically what the tasks are, it's useful to think about this. So here an aggregate is essentially, we can think of a binary operator that works on this array of the join output. And this binary operator can be either a sum, a min, a max, or whatever other aggregate operator you can think of. And this can get more complex. Of course, you can have group bys or more complicated aggregations. Now, to illustrate that this can actually work and we can speed up this aggregate computation, here is an example, a toy example that shows that for this query here, we have a binary join and every tuple has a weight column, this W, and we are interested in the weight of the minimum weight of the join answer. And so we can write a very simple query here in SQL. And this query, if we run it in Postgres here, this will be rather slow. So if here you can see if we just have 10,000 tuples, it already takes 10 seconds. But if we give the optimizer a hint of how to avoid materializing the join, you can see you can get a huge improvement here and do it in only 3 milliseconds. So this is something that already database systems can perform, and the optimizer should take into account these transformations. Now, another task we are interested in is unranked enumeration, where basically, if we think again of the implicit array of the join, we want to enumerate answers one by one in any order. Why would we want to do this? Because the output of the join can be extremely large. So if we try to compute it all at once, it can be very, very slow. And enumeration can help us with that by returning some answer very early and without computing the entire array here. Here's a small experiment where we have on the x-axis the time and on the y-axis the number of returned answers. We can see that this is a query that joins 4 relations, and the batch approach, which is essentially to compute the join, takes around 10 seconds here to compute everything. But enumeration can already start returning answers very, very quickly at 0.2 seconds, and it finishes in a time that is only 4 times larger. Now, ranked enumeration is the case where we also have a ranking function over the output, and the join answers are ordered by this ranking function. And the standard way to do this is first to sort the array of answers, and then what we want to do is basically to enumerate now, but in this sorted order. So we want to prioritize the query answers that are more important. And this measure of importance, you can think of it as it can be application dependent. So it can be, for example, how recent a tuple is, or some measure of quality. So you can think of this ranked enumeration essentially as an incremental sorting of the join output. Here's again an experiment where we can see initially again we have here batch and the unranked enumeration. Now, if we try to sort the output of the batch algorithm, you can see it takes around 6 seconds, and if we in our environment, that is, and in PostgreSQL, it takes around 11 seconds. But ranked enumeration can start returning the top answers very, very quickly, in 0.02 seconds here, and not only is it faster in the beginning, but you can see here that it's actually faster also at the end. And this is not an accident. We will see later how this is possible and how we can exploit certain properties of the join to do the sorting faster. A special case of ranked enumeration is the well-known top K paradigm, where we want the top K answers. And this is essentially the special case where we have a fixed cutoff, and we don't really care about enumerating. We just want the top 3 answers here. And essentially, we have a limit K in the query. Selection is the task where we want to find the query answer at some specific position of the array. For example, to find the median or some quantiles. Now, the naming of selection is quite unfortunate because it can be confused with relational algebra selection in the database world. But unfortunately, that's the name we have from classic works on linear time, median finding, and so on. Direct access is the task where we want to handle multiple of these selections. So, and we want to build a data structure that can handle these accesses more efficiently than handling its access one by one. Now, to be more specific, tractable selection would be the case where the time required to do it is very close to the database size and not the output of the join. And similarly, tractable direct access is the case where we can construct a data structure in time that is close to the database size and can allow this access is very efficient. Let's look at an example. Here we have a binary join between R and S. And for this example, we have columns A, B, C, and these weights. So if we want to do direct access by the lexicographic order A, B, C, then this can be done in a tractable way. But if we want to do now the lexicographic order A, C, B, this is not possible. And intuitively, that's because B is in the middle, and we have to go back and forth. But selection is possible for this lexicographic order. So basically, one access only, let's say the median. And now if we switch the ranking function and we look at the sum of weights, direct access is not possible for this binary join, while selection is tractable. And we have explored in detail the cases where exactly which queries are tractable and which aren't, and we have come up with very precise dichotomies. Now, the final task we are interested in is the special case where there's no task over the join and we're just interested in producing the output of the join. In this case, what we want to do is avoid as much as possible unnecessary intermediate results. And here's a small example again, where we have a join between 3 relations. And if you look at this example closely, you will see that it actually has only one output tuple, the join, and it's this the zeros here. And the database is not, PostgreSQL in this example, is not able to do it efficiently. So if we write a simple query, here it essentially does quadratic computation. But if we write an equivalent query, but with some hints to the optimizer of how to avoid intermediate results, then this can be done much, much more efficiently in linear time in the side of the database. And we will see later in the tutorial exactly how this works. Now, let's look at how to measure success for these techniques. We will be using basically the standard big O and big omega complexity notations and the standard RAM model of computation. We have the size of the database, which we will be using the N symbol for that, and the size of the query, which we will be denoting by L. And finally, we have the size of the output, which is R. Most of the results we present in this tutorial are in data complexity, which means that we consider the size of the query to be constant. So this means that the users don't write arbitrarily long queries, but we're mostly interested in the scalability in the size of the data. And this helps simplify some formulas. For example, if we have some factors that only depend on the query, this can be removed. We also have this O tilde notation, or soft O, which removes polylogarithmic factors. So if we have some logarithm to the power of some query-dependent function here, then this can be removed with the soft O. Now, if we look at the join of L relations, in general, this can have the size of its output can be n to the power of L asymptotically. But ideally, what we want to do instead is to have running times for all the tasks that we discuss, which are closer to the database size, which is linear, order n. Some assumptions that we use are that there are no pre-computed data structures like indexes, and we mainly focus on in-memory computation, so we don't consider an I/O model. And for our analysis, we also assume that hash tables support constant time lookups. Otherwise, the formulas have to be modified, essentially multiplied by some logarithmic factor. Now, with this model, linear time order n, you can think of it as for free, because we can't avoid looking at its input tuple once because we don't have any indexes. And so doing a constant 2 or 3 or 4 passes over the database is for free in this model. Now let's look at the measures of success for enumeration algorithms. And here there are 2 ways to measure success. One is the time up to the kth answer. And the second one is the time that's required for preprocessing, and then the worst case delay between 2 consecutive answers. Why do we care about the delay? Well, delay can be useful if we want to get a bound on the time to k. So if we know that delay is bounded by something, then we can derive a corresponding guarantee for the time to k. However, you can see that low delay is sufficient but not necessary in order to get a low time to k. And you can see here on the right an example where we have 2 algorithms, A and B. And A is faster than B here for because it returns every answer faster than B. But you can see that from the 4th to the 5th answer, we have a high delay. But it doesn't matter if we are just interested in getting the fastest algorithm possible, because the lowest delay doesn't necessarily mean a faster algorithm. Now, if we take an algorithm that has low time to k, it's also possible to derive another algorithm that has low delay. This is possible by holding the answers in a buffer and returning them back to the user in regular inter-arrival times. Of course, if we do this, it slows down the algorithm, so it's not something we want to do if we are interested in getting the fastest possible algorithm. So when would a low delay algorithm be desirable? 2 things need to hold. So we need an application that requires these regular inter-arrival times, and also some setting where there's not enough space to buffer the answer so that we can apply this technique here. And people have gone to long lengths in the literature in order to achieve these low delay algorithms, but this is it's a more restricted requirement than time to k, which doesn't have that many practical applications. Okay, now let's look at an overview of all the techniques that we will be discussing in the tutorial. I will be giving the high-level ideas, so basically what its technique is and why do we care about this? Why is it useful? And we will discuss in the later parts more details about these techniques. The first one is factorized representations. So what is the key idea? The idea is to represent the answers of the query in a very compact way that is also lossless, and it allows the other tasks, the tasks that we are interested in, to be done directly on this representation. These representations essentially form the basis for everything that we discuss in this tutorial, such as enumeration, direct access, and all the other tasks. Where does the name factorized come from? It comes from algebraic factorization, where basically what we do is we take a formula and we pull out the common factors. And what this essentially does is it makes the formula more compact. So you can see here we have 4 elements and 3 operations. And from that we go to 3 elements and 2 operations. So this basically makes the formula shorter. That's also something that we want to do now for query answers. We can do something similar. Because query answers have redundancy, especially the answers of a join, and this redundancy can be factored out. More specifically, if we have a query which runs on a database of size order n, we can, as we said, we can get an output that has a size of n to the power of n in the worst case. And what we want to do is to build a representation directly from the database that is much smaller than the size of the join output. This representation also needs to be lossless, which means that from the representation we can reconstruct all the query answers back. The size of this representation, as we will see, is linear, so the same essentially as the database for equijoins. And we will also look at constructions that can do something similar for inequality joins by only increasing the size by some polylogarithmic factor. And for general theta joins, it's going to be quadratic. The next topic we will be looking at is acyclic queries and the Yannakakis algorithm. So what is this about? Basically the queries that are acyclic are those that can be handled without having to do any cyclic joins. And these are the queries that form the basis of all efficient evaluation. And they have the property that we can remove in linear time all the input tuples that don't participate in any output tuple. And that's very powerful. The Yannakakis algorithm exploits this property and answers acyclic queries in essentially optimal time, which is n plus r. So basically the size of the input plus the size of the output, and you can't do better than that. If we are given a query, we can tell if it's acyclic or not by constructing a join tree. A join tree is a tree where the nodes are the relations. And it also satisfies one more condition, which is that the nodes that contain the same variable, the variables are the columns here, have to be connected in the join tree. So you can see here that for example, all the nodes that contain P are connected in the join tree. If you compare now the join tree to a standard query plan that the database uses, basically the join tree only gives a partial order for the joins. It only tells us that, for example, here we have to do TR or TS before we do T join U. So the Yannakakis algorithm uses the join tree to do 2 passes over the database, one bottom up and one top down. And with this process, with these 2 scans over the database, it removes all those dangling tuples that are not needed for the output. And subsequently, all the joins that we do following the order of the join tree can never produce any unnecessary intermediate results. Now let's look at projections. Projections can make things more difficult because when we project out a column, we can get many duplicate rows, and thus it can be even more difficult to avoid these unnecessary intermediate results. Let's look at an example query here, where we have xy YZ, ZU, and we project out the column X. This projection is easy because we can apply it to the base table R before we do any of the joins. But now if we look at another query which has the same joins but also projects out the column Y, we can see that we can't do the same trick again because Y is needed for the join between R and S. So we can apply it only after we join R and S, which can take quadratic time. Now, the Yannakakis algorithm, as well as enumeration and other tasks such as direct access, for these tasks, there are easy and hard projections. And the easy cases are captured by a class of queries which are called free-connex. And without going into the definition of what these queries are, one way to think about them is that they allow us to eliminate all the projections in the query in linear time. If we are given a query with projections that is free-connex, then we can transform it into a query from Q to Q prime, which has no projections, and it's evaluated over a database D prime instead of D, but that has the same size asymptotically as the original one. And so here in those examples, both those queries are free-connex, which means that for the second query, we can apply this linear time transformation to get another query Q prime, which produces exactly the same answers and doesn't have any projections. Now, for queries that are not free-connex, this trick doesn't work, and it doesn't work provably under some hypothesis in fine-grained complexity. Another technique that we will be looking at is dynamic programming. Dynamic programming is very well known. It's the archetypical way of handling problems that have a shared structure. For example, the Bellman-Ford algorithm is an example of dynamic programming. It computes the shortest path from a source to a target in a direct acyclic graph in linear time and the size of the graph. And the way this works is that we go essentially bottom up from the target to the source, and for each node we compute the optimal cost to reach the terminal, the target. The reason that this works is that the problem here has a shared structure. Different paths share common edges in the graph, and that's why dynamic programming can be efficient here. But we also want now to do the reason that dynamic programming is also relevant for queries, specifically for computing aggregates, is that the queries also have a shared structure. And the shared structure is given exactly by the factorized representation. Basically, in the same way that paths in the graph share common edges, if you output tuples of a join share the common input tuples. So as an example here, we can have two output tuples, R1, S1, T1, R1, S1, T2, and you can see that they share the same input tuples R1, S1. Dynamic programming can help us compute in linear time for acyclic queries many different tasks. For example, the count of query answers, or what is the query answer with the minimum sum of weights, or what is the query answer with the highest probability of being true. And all of them are computed by the same algorithm. And the only difference is that we have to swap operators. So the first one is computed with operators plus and times, the second one with min and plus, or max and times for the third one. The reason that this is possible is that these operators share the same algebraic properties. And these properties are described by algebraic structures that we call semi-rings, and we will look at them more deeply in the later parts of the tutorial. NK is a technique that we have developed to perform ranked enumeration. And the key idea is that if you take a problem where we can apply dynamic programming, then we can also find the second and the third best solution to that problem. So basically to do ranked enumeration for dynamic programming. if we look at algorithms, at any k algorithms, there is an algorithm that is faster for small values of k, when we want few answers in the output, and another one that becomes faster as the value of k increases. And in our latest work, we have developed an algorithm that achieves the best of both worlds. Now, these algorithms can be used for any problem solvable by dynamic programming and not just joins. So, for example, you can apply it to the problem of longest increasing subsequence, the knapsack problem, or whatever problem your favorite DP problem is. NK allows us to do ranked enumeration in a time that, if we look at data complexity, is only slower by a logarithmic factor than unranked enumeration. So while unranked enumeration for free-connex queries can be done in time that basically takes linear time in the beginning n, and then only k, which is the number of returned answers, ranked enumeration only adds a logarithmic factor, and we can get this prioritization of query answers. Also, perhaps surprisingly, when we return the last answer, some NK algorithms can be even faster than generic comparison-based sorting, like, let's say, merge sort. And we saw that before in the experiment that I showed. And the reason is that query answers are not independent; they have a shared structure, and so we can use comparisons. We can store comparisons and reuse them to speed up the sorting. So, for example, we have here an example of 4 paths that share 2 prefixes p1, p2, and suffixes s1, s2. By comparing the suffixes, we can infer the relative order of the paths more efficiently. Worst-case optimal joins is another research area that has been investigated a lot recently. The key idea is that binary join plans in databases can be proven to be suboptimal for cyclic queries because they can take more time than the worst-case output. For example, if we look at the triangle query, where we have x, y, y, z, and z, x, so x is basically here, creates this cyclic pattern. Any binary join plan that you can think of will take unavoidably quadratic time in some database, but the worst-case optimal join algorithms can do this in just n to the 1.5, which is asymptotically better. And for every query, we can basically find what its worst-case output is. That's now known as the AGM bound by the names of the authors that came up with this. And there are algorithms that match this bound. The worst-case optimal joins essentially match this worst-case bound for every query. Finally, hyper-tree decompositions, or tree decompositions for simplicity, is a technique that allows us to take a cyclic query and transform it back to the acyclic case. So basically, we start with a query that has cycles, and it's over a database with size n. And by applying these hyper-tree decompositions, we can get another query that doesn't have cycles. It's acyclic, and the cost we pay is that we have to materialize some new relations, and those relations are bigger than order n. They can be n to the power of d, and this d is a parameter of the decomposition called the width, and it basically measures how expensive is this decomposition. We will be looking in more detail into this technique now in the second part. So I think, Mirek, I will pass it on to you to discuss tree decompositions and how to handle cyclic queries in general.